one wavefront on the following, the source traveled a distance given by v times the time between wavefronts. What's the time between wavefronts? The time between emissions is 1 divided by the frequency, because this is a number of seconds. And so remembering that lambda times f is c, I can write f as c over lambda, and I get lambda is lambda 0 minus, let me write this correctly. Lambda is lambda 0 minus v lambda 0 over c, or Doppler's formula, lambda is lambda 0 times 1 minus v over c. Notice that this v was taken to be positive when the source was approaching the observer. An observer on this side, of course, sees the wave dilated. The wavelength looks longer, the pitch is lower as the car is receding from you. Each subsequent wavefront has a longer distance to go. That is compensated in this formula by considering v to be negative if the source is receding and positive if the source is approaching you. We talked about heat energy, and we need a few properties of heat, because heat will be a dominant form of energy in some environments that we talk about. And so it's a property of heat that if you have a hot object and a cooler environment, then the hot object will lose energy to the environment, and this process will continue indefinitely or until such time as the temperatures equilibrate, because as the source loses heat, the environment gains heat and warms up, and eventually, if the temperatures are equal, then we have equilibrium and heat flow stops. But so long as you have a warm sun in cold space, the sun will continue to lose heat to space, and until such time as either space heats up or the sun cools down, this process will continue. There will be a constant flux of energy out of the sun into space. And there are several ways by which this transfer of heat from a hotter to a cooler body can occur. One is called conduction. This is where heat is transferred through continuous contact, and this is not in great importance in astronomy. Heat conduction on astronomical scales is rare. A second phenomenon is convection. This is basically like trucking. This is what happens when the physical motion of the fluid carries energy. This works very well if you have a volume of fluid that is heated from below. That happens when you boil water on your stove. It also happens in stars, say, where a hot core is heating the atmosphere from the inside. What happens is that at the bottom of the pot or the bottom of the atmosphere, the fluid is heated. The heated fluid expands. The expanded heated fluid is lighter, less dense than the surrounding fluid. It therefore floats to the top and rises. Cooler fluid descends to take its place, and what you have is an energy transfer from the bottom to the top by heated fluid physically moving from one part to the other. And this does occur in astronomical phenomena. None of this, of course, is helpful to the sun in losing its energy to space, because the sun is not in contact with anything, nor is there any fluid around it to convect. The way the sun loses energy to space is radiation. It turns out that every object, unless it's at zero temperature, glows, and that mechanism of energy loss is radiation heat transfer, and essentially the radiation in question is sunlight. Sunlight is the way the sun attempts to heat up space, losing energy because it's warmer, and we'll come back to this calculation in a moment, but let's understand something about this heat flux, energy flux problem. And so the sun is hot, and so it radiates, and we'll learn how to compute how hot it is and how much it radiates. But for now, let's assume that the sun is radiating energy at a constant rate. Why is the rate constant? Because the properties of the sun are unchanging, the properties of space are unchanging. So the rate at which the sun loses energy to space is therefore unchanging. We call that rate the luminosity, and it's measured in joules per second, in watts. The sun, like a light bulb, produces a certain amount of energy, or loses a certain amount of energy to space every second, and we'll figure out this number. Obviously, it's a great many light bulbs. Now, what interests us often is how bright the sunlight is at some given location in space, and what that implies is put some uniform detector, say an eye with a fixed surface area, and as we saw, or as this diagram shows, if this is something the size of your eye or of your detector, the farther it goes, the less sunlight it traps, because essentially the sun produces radiation in all directions, and so at any distance, the sunlight is spread uniformly across the surface of a ball or a sphere of radius r. And if you are at some distance and you place your detector takes up some fraction of that sphere. If you are twice as far, the sphere is larger, and your detector now takes a smaller fraction of this larger sphere, and the result will be that your detector, since all of the sun's rays pass through this sphere, and all of the sun rays a little later pass through this sphere as well, the net total amount of energy passing through each sphere is the same, but the total amount passing through a fixed detector decreases because the spheres grow larger, whereas the detector does not. Mathematically, the statement is that at a distance r, the radiation is distributed uniformly on the surface of a sphere, so energy per second received by a square meter of detector will be the luminosity divided by the surface of a sphere across which the radiation is spread uniformly. And so the sun energy is diluted by a factor of r squared as it travels out into space. Light, of course, is going to be of incredible importance in our understanding of the universe. It's the main way we perceive our environment on Earth. It is certainly the main way that we receive information from distant places in the universe, so the properties of light will be extremely important to us. So light, of course, is the main way we as humans perceive the world around us. It's also the main way that we as astronomers learn about distant objects. The nature and the properties of light are going to be extremely important to us. And the first of these is the speed. So light carries energy away from the sun to Earth to warm us. And the speed at which light propagates is huge. It's about 3 times 10 to the 8th meters per second. This large number makes accurate measurement difficult. First really good measurement was in 1850 by Foucault and Fizeau, though there were earlier less precise measurements. Now, in a classic experiment in 1670, our old friend Newton made the discovery that the sunlight, white, colorless light from the sun, in fact contains all colors of light. He found a way to split a beam of white light into beams of various colors. He was using a prism. Today we use a diffraction grating. And he conjectured that the nature of light was a stream of particles. Of course, he had all the mechanics know-how to understand a stream of particles. Light moved in straight lines, like particles upon which no forces act, moved at a constant velocity. It seemed a lot like a mechanical particle model of light would be likely. This is one of the rare cases where Newton was wrong, because in 1799, only 120 years later, Young observes light waves interfering. So he makes the observation that you can take light and you can construct these interference effects where light waves add and subtract and you get nodes. This interference was a hallmark of wave phenomena, so Newton for once was actually wrong. Light is a wave. But never count Newton out. We'll come back to this point in the next clip. And that same Young, 3 years later, shows that our eyes, while they are extremely accurate in giving directional perspective, so they tell us very precisely which direction light is coming from, that's how we construct our image of the world, are in contrast relatively poor as Fourier analyzers. Unlike our ears, which can distinguish a great variety of sounds and hear several simultaneous tones and distinguish them, our eyes are a very poor Fourier analysis machine. They only are sensitive to the relative intensity of 3 colors, red, green, and blue, and we'll see in a minute what that leads to. What we're going to do is an experiment somewhat similar to what Newton did. So we have here a beam of white light, and we're going to put a diffraction grating in front of it, and the diffraction grating splits the white beam so that the white stripe in the center is somewhat dimmed, and on both sides we find the familiar rainbow structure. And so we see a stripe of red flaring to orange and yellow and green and into blue and violet. And we can see what happens when we put a filter in front of the light, we get red light. And when we feed red light into the diffraction grating, what we see in the spectrum is that the green and the blue are missing. Similarly, when we feed green light into the diffraction grating, the blue and the red are missing and only green light comes in. So the diffraction grating is not coloring the light, it is deflecting whatever green light it gets to that region. Again, putting a blue filter in front of the beam, we see that only the blue remains in the spectrum. The blue filter absorbs the green and the red, the green filter absorbs blue and red, and the red filter absorbs green and blue. These are, it turns out, the primary colors. It has to do with our eyes. Here's what happens when you put a cyan filter in front. A cyan filter absorbs the red light and so lets through the blue and the green. Similarly, if we use a magenta filter absorbs the green, letting through the blue and the red. So what we see as magenta is blue light and red light. There is also, we can put a yellow filter in, and this is important. We see that what we perceive as yellow light is, in fact, light that is missing its blue. The green and the red are present, the blue is absent, and we see yellow. And so if we superpose the yellow and the magenta filters, the yellow filter absorbs the blue, the magenta absorbs the green, and what is left is red. And indeed, superposing those two filters, we get red. If we superpose yellow and cyan, the yellow absorbs the blue, the cyan the red. What's left is the green, and we see that very nicely in this picture. And we can keep playing. We can superpose the cyan and the magenta. The cyan absorbs the red, the magenta absorbs the green.